Welcome to chemistry class, my dear students. Today we are going to take up the concept of periodic classification of elements. Till date, 110 elements have been identified. Out of 110 elements, 6 elements are chemically non-reactive in nature. So, remaining 104 elements, they react among themselves and with each other to form number of compounds. In order to remember the properties of all those elements and compounds is a Herculean task. That is why the elements have been classified in a systematic manner successfully by a scientist called Moseley. Moseley's experiments are based on X-ray preparation experiments. X-rays are generated by using a discharge tube called as Coolidge tube. In this discharge tube, two electrodes will be present. One is a cathode, another one is anode. To the anode, target element is fixed. X-rays are generated by making use of Coolidge tube. Coolidge tube is a normal discharge tube fitted with two electrodes. One is cathode, another one is anode. Moseley's periodic classification is based on X-ray production experiments. X-rays are generated by making use of Coolidge tube. Coolidge tube is a normal discharge tube consisting of one cathode and one anode. Anode is fitted with a target. When high voltage current is passed from the cathodic end, rays are generated which, when strike the target element in the perpendicular direction, invisible electromagnetic rays will be generated. Rontgen has named these rays as X-rays because at his time existence of these types of electromagnetic waves was unknown. Moseley, what has done is he changed the target element. At the time of Moseley, 32 elements were known. With each element, a new target is made and X-rays were produced. What he has observed is, whenever the target element is changed, the frequency of X-rays generated was changing. Then he correlated the relation between frequency of the X-rays generated and the atomic number of the target element. The correlation that he found was square root of mu is equal to A into Z minus B. Here mu is called frequency of the X-rays generated, A and B are called as Moseley's constants and Z is called atomic number of the element. So, from this relation he pronounced the modern periodic law, which says the physical and chemical properties of elements are dependent on atomic number of the element. So, based on this law and concepts of atomic structure, Moseley has arranged all the elements available at his time in the form of a tabular form, which is called as Moseley's periodic table, or it is also known as Moseley modern periodic table. While constructing the periodic table, Moseley has made use of Niels Bohr's atomic model, as well as in the arrangement of elements. Strictly he followed 𝗹𝗶𝘁𝗶 principle. Hence, modern periodic table is also called as Bohr's periodic table as well as 𝗹𝗶𝘁's periodic table. In the periodic table, elements are arranged in horizontal rows and vertical columns. Horizontal rows are called as periods. Vertical columns are called as groups. A total of 7 periods are present in the modern periodic table and 18 groups. In every period, one particular energy level will be gradually filled with electrons, and in a particular group, elements with a similar outer electronic configuration are placed. The first period begins with hydrogen and ends with helium. In the first period, first orbit will be gradually filled with electrons. In the first orbit, a maximum of 2 electrons can be placed. That is why the number of elements in the first period are 2. Hydrogen, helium. Hydrogen atomic number is 1, helium atomic number is 2. Then second period, second orbit will be gradually filled with electrons. In this period, a total of 8 elements have been placed. Lithium is the starting member, atomic number is 3. Neon is the last member of the period, whose atomic number is 10. Third period begins with sodium, whose atomic number is 11, ends with argon, whose atomic number is 18. In the fourth period, starting element is potassium, ending element is krypton. In the fifth period, starting element is rubidium, ending element is xenon. In the sixth period, starting element is cesium, atomic number 55, ending element is radon with atomic number 86. The seventh period begins with francium, atomic number 87, and stops at atomic number 118. So, in the first period, a total of 2 elements are present, second period 8, third period also 8, fourth period 18, fifth period 18, sixth period 32 elements. The seventh period is incompletely filled with the elements because some of the elements are to be discovered yet. These numbers 2, 8, 8, 18, 18, 32 are called as magic numbers in the periodic table, because at these intervals of atomic numbers, the properties of elements get repeated. Based on the number of elements present in each period, they are given specific names. As the first period consists of only 2 elements, it is known as shortest period. The second period is known as first short period. Third period is known as second short period. The fourth period is called as first long period. Fifth period is called as second long period, and sixth period is called as longest period. The seventh period, it is known as incomplete period. So, in order to easily remember the starting element and ending element in any period, just we have to remember the elements of first A and 0 group elements, because every period begins with 1A and ends with 0 group. The practical use in the examination point of view is the range of atomic numbers can be used to identify the period number of a given element. Say for example, what is the period number of an element with atomic number 92? So, you can easily identify by remembering the range. 92 comes in between 87 and 110. So, the element with atomic number 92 belongs to 7th period, you can say. Say for example, if any element's atomic number is 84 and you have to identify the period number, you can see 84 lies in between 55 and 86. Therefore, the element with atomic number 84 will be present in the 6th period. Like this, period number can be identified by remembering this classification of elements into periods. The elements with a similar outer electronic configuration were placed in one particular group. So, you can say this classification is based on electronic configurations of elements. The 18 groups are classified into two types as A type and B type. In A type of groups, the differentiating electron enters into the outermost S and P sublevels, whereas in B type of groups, the differentiating electron enters into penultimate D sublevel. Here, you should be clear with the terms like differentiating electron, outermost orbit or shell, penultimate orbit or shell, and anti-penultimate orbit or shell. The electron which makes the difference between two elements is called as differentiating electron. Say for example, what makes the difference between the elements hydrogen and helium? Hydrogen atomic number is 1, that means it has got 1 electron. The atomic number of helium is 2, that means it has got 2 electrons. So, the second electron makes the difference between hydrogen and helium. So, in case of helium, second electron will become the differentiating electron. Similarly, in case of other elements also. Then, the last orbit in which electron is present is called as outermost orbit. Generally, this is denoted with the letter N. Then, towards the nucleus next to the outermost orbit is called as penultimate orbit. It is denoted with the symbol N-1. Next to the penultimate orbit is called as anti-penultimate orbit. It is denoted with the symbol N-2. So, depending on the position of differentiating electron, all the 18 groups have been classified into two types as A type and B type. If the differentiating electron enters into the outermost S and P sublevels, then those elements are called as A type of groups. If the differentiating electron enters into the penultimate D sublevel, they are called as B type of groups. An S sublevel can accommodate maximum of 2 electrons, whereas P can accommodate 6. So, a total of 8 electrons can be accommodated in S and P sublevels taken together. That is why there are 8 A type of groups, and these are numbered as 1A, 2A, 3A, 4A, 5A, 6A, 7A and 8th A. 8th A is also called as 0 group. Similarly, a D sublevel can accommodate a maximum of 10 electrons. That is why there are 10 B type of groups, and these are named as 3B, 4B, 5B, 6B, 7B, 8B, 1B and 2B. That means there is no sequence order in the B type of groups. Begins with 3B, continues up to 8B and ends with 1B and 2B. To avoid this confusion, EAPCET has suggested the usage of normal integers in the sequential order. So, according to which 1A group is called as first group, 2A is called second group, 3B is called as third group, 4B is called as fourth group, fifth group, sixth group, seventh group. In the 8th B, there are 3 groups clubbed together. That is why they are numbered as 8, 9, 10. 1B is called as 11th group, 2B is called as 12th group. 3rd A is 13, 14, 15, 16, 17 and 18. So, that is the suggestion given by EAPCET to indicate the groups present in the periodic table. The 1A group elements, they are called as alkali metals, 2A group elements are called as alkaline earth metals, 3A group elements are called as boron family, 4A group elements are called as carbon family, 5A group elements can be called either as nitrogen family or as nicogen family. Nicogen means bad smelling, because elements of 5th A are related to compounds which are having bad smell. That is why this group is called as nicogen family. Then 6th A can be called as either oxygen family or as chalcogen family. Chalcogen means related to ores. Most of the 6th A group elements are associated with minerals and ores. Hence, that group is also called as chalcogen family. 7th A group elements are popularly known as halogens. Halo means deep. Most of the halogens, most of the 7th A group elements are available in nature in the form of salts in sea water. Hence, they are called as halogens or halogen family. Then the elements of 0 group are called as inert gases because of their chemical inertness under normal conditions. As far as the B type of groups are concerned, no such specific names are given. Only 1B group elements are given a specific name called as coinage metals. The elements present in 1B are copper, silver and gold. These 3 metals were earlier used in the making of coins. That is why they are called as coinage metals. These are also called as typical transition metals. That is the classification of elements into groups. A further detailed study of groups can be done in this manner. The A type of groups: 1A, general electronic configuration is NS1. Elements present in this group are hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. 2A group elements, general electronic configuration is NS2. The group begins with beryllium, magnesium, calcium, strontium, barium and radium. The 3rd A group elements general configuration is NS2, NP1. The group begins with boron and continues with aluminum, gallium, indium and thallium. The 4th A group elements general configuration is NS2, NP2, carbon, silicon, germanium, tin and lead are the elements present in this group. In 5th A, the general electronic configuration is Ns2Np3. Elements present are nitrogen, phosphorus, arsenic, antimony and bismuth. In the 6th A group, the general electronic configuration is Ns2Np4 and elements present are oxygen, sulfur, selenium, tellurium and polonium. The general electronic configuration for 7th A group elements is Ns2Np5. Elements present are fluorine, chlorine, bromine, iodine and astatine. In the 0 group or 8th A group, the general electronic configuration is Ns2Np6. However, the starting element helium has got a configuration of 1s2 only. This configuration is called as doublet configuration. Rest of the elements neon, argon, krypton, xenon and radon have Ns2Np6 configuration, which is commonly referred to as octet configuration. Elements with either doublet configuration or octet configuration are chemically stable in nature. That is why 0 group elements are non-reactive in nature under normal conditions. Then in the 1st A group, hydrogen is a non-metal. Except hydrogen, rest of the elements are metals and they are strongly basic in nature. That is why 1A group elements are known as alkali metals. In the 2A group, all elements are metals. They are also basic in nature and are widely distributed in the earth's crust. That is why they are known as alkaline earth metals. In 3rd A group, boron is a non-metal. Remaining elements are metals. In 4th A, carbon, silicon are non-metals. Germanium is called semi-metal or metalloid. A semi-metal or metalloid will have 50% ionic character and 50% covalent character. Tin and lead are typical metals. Then in the 5th A group, nitrogen, phosphorus are non-metals. Arsenic is a semi-metal. Antimony and bismuth are treated as metals. In the 6th A, oxygen, sulfur are non-metals. Selenium, tellurium are semi-metals. Polonium is the metal. In the 7th A group, fluorine, chlorine, bromine, iodine are non-metals. Astatine is a metal. In the 0 group, helium, neon, argon, krypton, xenon, these are all non-metals and radon is a metal. So, as we see, as we move from 1st A to 0 group, the number of metals in individual groups are decreasing and non-metals number is increasing. So, you can say as we move from left to right in the periodic table, the metallic character decreases, non-metallic character increases. Particularly in the from 3rd A group to 7th A group, if we draw a diagonal like this, the elements which are present above the diagonal are generally non-metals. The elements which are present below the diagonal are generally metals and the elements which are present along the diagonal are considered as semi-metals. So, that is a classification of elements into groups, that too A type of groups. The detailed study of B type of groups. In the B type of groups, there are a total of 10 groups. However, the B type of groups are studied in the form of 4 series called transition series. In the first transition series, 3D level is gradually filled with electrons. That is why first transition series is also called as 3D transition series. In each transition series, a total of 10 elements will be present. The first transition series begins with scandium and ends with zinc. The second transition series, which is also called as 4D series, begins with yttrium and ends with cadmium. Third transition series, which is also called as 5D series, begins with lanthanum and ends with mercury. Fourth transition series, also called as 6D series, begins with actinium and ends in the middle itself, because some of the elements are to be yet discovered. So, that is why this fourth transition series is also called as incomplete transition series. As far as the electronic configuration is concerned, for third B group elements, the electronic configuration is n-1 d1 ns2. It will continue, and in the 2B group it will be completed as n-1 d10 ns2. That is the variation of electronic configuration. So, overall, if we look at the sequential order of groups, the groups can be represented like this: 1A, 2A, 3B, 4B, 5B, 6B, 7B, 8B, 1B, 2B, 3A, 4A, 5A, 6A, 7A and 0 group. That is the sequence order of groups. According to IUPAC convention, they can be numbered like this also. In the 8th B group, a total of 8 groups are present, which are represented as 8, 9 and 10, 11, 12, 13, 14, 15, 16, 17 and 18. So, by using this convention, we can locate the position of a group based on atomic number. In any period, atomic number increases by 1 unit in a successive manner. Therefore, in first A group element, first element's atomic number will be 1 and the last element in the first period will be 2. In the second period, element belonging to 1A group will have an atomic number of 3 and in 0 group an atomic number of 10. In between, the atomic number increases by 1 unit. So, one more thing what we have to remember is, in the third B group, the elements present are scandium, yttrium, lanthanum and actinium. But along with these 4 elements, a total of 28 elements are clubbed together. Along with lanthanum, 14 elements are placed together, and those 14 elements are called as lanthanides. Similarly, along with actinium, 14 more elements are clubbed together and they are called as actinides. The lanthanides begin with the element cerium with atomic number 58 and with lutetium atomic number 71. Actinides begin with thorium atomic number 90 and with lawrencium atomic number 103. So, these lanthanides and actinides, they belong to the same group 3B. That means, in 3B, in total number of elements present are 28 plus 4, 32. and the lanthanides, they belong to 6th period and 3rd B group, whereas actinides belong to 7th period and 3rd B group. So, longest group is the 3B group, whereas longest period is 6th period. Incidentally, in both, the number of elements present are 32. Further classification of elements. The elements present in the periodic table are classified in various manners. One type of classification is classification of elements into blocks, namely S block, P block, D block and F block. This classification of elements is based on position of differentiating electron, that is electron present in the outermost orbit, or the last electron of an element can be called as differentiating electron. Depending on its position, this classification is done. If the differentiating electron is present in the outermost S sublevel, they are called as S block elements. If the differentiating electron is present in the outermost P sublevel, they are called as P block elements. So, S and P blocks involve position of the differentiating electron in the outermost orbit, whereas in case of D block, the basis is position of differentiating electron in the penultimate D sublevel. N-1 shell is called as a penultimate shell. The F block elements include elements in which differentiating electron enters into the anti-penultimate F sublevel. Which is represented by the general formula N-2F. So, in an S sublevel, a maximum of 2 electrons can be accommodated. Accordingly, the S block consists of 2 groups. The groups present in S block are represented as 1A and 2A. Graphically, S block is present at the extreme left side of the periodic table. The elements of 1A are called as alkali metals, whereas 2A are called as alkaline earth metals. The general electronic configuration of 1A group elements is NS1, and general electronic configuration of 2A group elements is NS2. That is why the general electronic configuration of S block elements means you should write NS1 to 2. Then coming to the general characteristics, the elements present in 1A are hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. Whereas in 2nd A, the elements present are beryllium, magnesium, calcium, strontium, barium and radium. Hydrogen is a non-metal and exists in the form of gas and mostly forms covalent compounds. It exhibits 2 types of oxidation states, +1 and -1. +1 in combination with the non-metals and -1 in combination with the metals. Coming to the rest of the elements, lithium, sodium, potassium, rubidium, cesium and francium all are metals. Lithium to cesium are normal metals, whereas francium is radioactive metal. In general, in any group, the last element will be radioactive in nature. All these exist in solid state. Cesium and francium, their melting points are too low. So, in some books they are referred to as liquid metals. Coming to their properties, these 1A group metals, they are highly reactive in nature and act as powerful reducing agents. Their compounds are mostly ionic in nature. Similarly, in the 2nd A group, all the elements starting from beryllium to barium exist in solid state as well as metals. Radium is another radioactive metal. Just like 1A group elements, 2A group elements are also involved in the formation of ionic compounds. These are also highly reactive in nature and form mostly ionic compounds in which they show a common oxidation state of +2. So, here the position of hydrogen in S block is somewhat anomalous, because most of the properties of hydrogen are different from rest of the elements of the same group. That is why till date position of 2 elements in the periodic table is uncertain. One is hydrogen, second one is helium. That is in short about the details of S block elements. Next is P block elements. P block elements. The elements in which differentiating electron enters into outermost p sublevel are called as P block elements. A p sublevel can accommodate a maximum of 6 electrons. Hence, in P block, number of groups present are equal to 6 and they are numbered as 3A, 4A, 5A, 6A, 7A and 0. 0 group is also referred to as 8th A group. The general configuration is NS2 is common for all the P block groups. For 3rd A group, the continuation configuration will be NP1. In 4th A, it is NP2, 5th A, NP3, NP4, NP5 and NP6. Therefore, the P block general configuration can be represented as NS2, NP 1 to 6. Coming to the general characteristics, the elements present in 3rd A group are boron, aluminum, gallium, indium and thallium. In 4th A, elements present are carbon, silicon, germanium, tin and lead. In 5th A, elements present are nitrogen, phosphorus, arsenic, antimony and bismuth. In 6th A, oxygen, sulfur, selenium, tellurium and polonium. 7A, fluorine, chlorine, bromine, iodine, astatine. In 0 group, helium, neon, argon, krypton, xenon and radon. Coming to their individual characteristics, boron is a non-metal. Aluminum to indium as well as thallium are metals, and all these elements exist in solid state and they mostly form covalent compounds. In 4th A group, carbon and silicon are non-metals. Germanium is a semi-metal. Tin and lead are metals and all are again solids. Germanium is a liquid semi-metal. In fact, this is the only semi-metal that exists in liquid state. Rest of the elements in 4th A group exists in solid state. Coming to 5th A group, nitrogen is a gas, phosphorus onwards exist in solid state. Both nitrogen and phosphorus are non-metals, arsenic is a semi-metal, antimony and bismuth are treated as metals. In the 6th A group, oxygen exists in the form of gas, rest of the elements exist as solids. Coming to their metallic and non-metallic character, oxygen and sulfur are non-metals, selenium and tellurium are treated as semi-metals, polonium is a radioactive metal. This element was discovered by Madame Curie and in the honor of her country is named as polonium. She is from the country Poland. Then coming to 7th A group elements, fluorine and chlorine exist in gaseous state, bromine exists in liquid state, iodine and astatine exist in solid state. From fluorine to iodine, the elements are non-metals. Astatine is again a radioactive metal. In the 0 group, helium to xenon are non-metals and exist in the form of gases. Radon is also a gas, but it is a radioactive metal. So, as we can see in the P block, there are non-metals, metals as well as semi-metals. We can see all the 3 types of physical states like solid state is there, liquid state is there, gaseous state is also there. The most important thing is the liquid elements are to be remembered. Germanium is the only liquid semi-metal present in the nature or periodic table, and bromine is the only liquid non-metal in the periodic table, and radon is the only metal that exists in gaseous state. Coming to their general properties, the P block elements starting groups, that is 3A, 4A and 5A, they mostly form covalent compounds, whereas elements of 6th A and 7th A, they form ionic compounds. 0 group elements are chemically non-reactive in nature under normal conditions because of their stable electronic configurations. So, that is the detailed study of P block elements. The elements in which differentiating electron enters into penultimate d sublevel are called as d block elements. The general electronic configuration of d block elements is n-1 d1 to 10 ns 1 to 2. A d sublevel can accommodate a maximum of 10 electrons. Hence, in this d block we will come across 10 groups. However, these elements are not studied group wise, but in the form of 4 series called transition series. In each series, 10 elements are present and a total of 4 transition series are there. First transition series, second transition series, third transition series and fourth transition series. The first transition series is also called as 3D series because 3D orbitals will be gradually filled with electrons. Second transition series is also called as 4D transition series, 5D transition series and 6D transition series. The 3D series begins with scandium and ends with zinc. Second transition series begins with yttrium and ends with cadmium. Third transition series begins with lanthanum and ends with mercury. The fourth transition series begins with actinium and will stop in the middle itself. That is why this fourth transition series is also called as incomplete transition series. There are no specific names to the D block elements or D block groups except 1b. In 1b, the elements present are copper, silver and gold. These are called as coinage metals because these metals are used in the making of coins. These are also called as typical transition metals. Then coming to general characteristics of D block elements, all the D block elements are metals. They exist in solid state except mercury. We all know mercury is a liquid metal. Then coming to other characteristic features, all the D block elements have got very high density values, melting point values, boiling point values. They are all good conductors of electricity. They are malleable as well as ductile in nature, and these D block elements show variable oxidation state values. Variable means each element can exhibit more than one type of oxidation state. That is because of participation of both outermost Ns electrons and in a stepwise manner penultimate D electrons. These elements show variable oxidation states. The highest oxidation state of +8 is observed in this block, and this highest oxidation state of +8 is shown by two elements. One is ruthenium, another one is osmium in their tetroxides. Along with this, most of the D block elements are colored. Not only the elements, their ions are also colored. Based on the color, we can identify the metals as well as their ions. Along with, the D block elements have characteristic magnetic properties also. They can exhibit diamagnetism, paramagnetism and ferromagnetism. The D block elements which do not possess any unpaired electrons, d electrons in particular, will be diamagnetic in nature. Whereas the elements or ions with one or two unpaired d electrons will be associated with a paramagnetic nature. If more than two unpaired electrons are present, then that element can exhibit ferromagnetism. The strength of the magnetism is expressed by means of a term called as a magnetic moment. This magnetic moment can be calculated by using this relation square root of n into n plus 2, unit is Bm. Bm stands for Bohr magneton. N corresponds to number of unpaired d electrons. So, how to identify the number of unpaired d electrons? That can be done by writing the electronic configuration. Say for example, if you take scandium, its atomic number is 21. Electronic configuration can be represented as argon 3d1 4s2. So, in the 3d level, one unpaired electron is present. Therefore, n value is 1. It can exhibit paramagnetism, and corresponding magnetic moment value is square root of 1 into 1 plus 2, that is root 3 Bm, you can say. So, in this way we can calculate the magnetic moment of not only elements as well as ions also. That is about D block elements. F block elements. The elements in which differentiating electron enters into the anti-penultimate F sublevel are called as F block elements. Configuration of F block elements can be represented as n-2 F1 to 14, n-1 D0 to 1, ns1 to 2. These elements do not follow the normal rules of writing the electronic configuration. That is why the general electronic configuration also looks somewhat abnormal in nature. The elements in which 4f sublevel is gradually filled with electrons are called as lanthanides. Lanthanides begin with the cerium, atomic number 58, and end with the lutetium with atomic number 71. The elements in which 5f sublevel is gradually filled with electrons, they are called as actinides. They begin with the thorium, atomic number 90, and with the lawrencium, atomic number 103. The lanthanide elements are also called as rare earths because their availability in nature is very less. In the actinide elements, next to thorium comes protactinium and then uranium. Only these three elements are available in nature. After uranium and up to lawrencium, the elements are man-made. Hence, those elements are called as transuranic elements. And all the actinide elements are radioactive in nature. The lanthanide elements have very high melting point and boiling point values and are tough metals because of their atomic radius and compact structure. As we move from cerium to lutetium, the atomic size as well as ionic size gradually decreases than expected, because in case of F block elements, the differentiating electron is entering into antipenultimate F sublevel, which is nearer to the nucleus. Due to decreased shielding effect and screening effect, the nuclear force of attraction is abnormally increased, and as a result their size is far less than expected. This decrease in size observed in case of lanthanides is called as lanthanide contraction. A similar decrease in size is observed in case of actinides also, which is called as actinide contraction. Both lanthanides and actinides show a common oxidation state of +3. So, that is about the classification of elements into SPDF blocks, which is purely based on the electronic configurations of elements. Classification of elements into different types based on their chemical properties. It is also in one way dependent on electronic configuration. Based on the properties, the elements are classified as representative elements. The elements of S block and P block excluding 0 group can be called as representative elements. They are so called because of their chemical reactivity. The general electronic configuration of representative elements can be represented as Ns1 to 2, Np1 to 5. These elements are highly reactive in nature and are responsible for most of the compounds that we observe. Hence, the name representative elements. They cover both metals, non-metals and semi-metals, and the nature of compounds is both ionic as well as covalent in nature. Coming to transition elements, all the D block elements excluding 2B group elements are called as transition elements. As per the definition, if the element possesses incompletely filled penultimate d sublevels either in the elemental form or in any one of its common ionic form, then it is called as a transition element. The general electronic configuration of transition elements can be represented as n-1 d129 ns122. So, the elements of 1b, if we take in the 1b group, we have copper, silver and gold. For these three elements, the general electronic configuration is n-1 d10 ns1. Therefore, in the elemental state, these elements do not possess incompletely filled d sublevels, but in one of their common oxidation state, that is +2, they exhibit the general electronic configuration of n-1 d9, which will have incompletely filled penultimate d sublevels. So, as they are satisfying the condition of transition elements in one of their common ionic state, the 1b group elements are called as typical transition elements. Their general characteristics are similar to that of d block elements. Then inner transition elements. Practically there is no difference between F block elements and inner transition elements, and zero group elements are called as inert gases because they do not participate in chemical reactions under normal conditions. So, this type of classification is based on chemical properties of the elements, we can say. So, these are the various ways of classifying the elements. The first and foremost one is classification of elements into periods and groups, which is done by Moseley based on atomic number of the elements. Further classification is classification of elements into SPDF blocks, which is based on electronic configurations, and the third type of classification is based on chemical properties. Of course, chemical properties of the elements are dependent on electronic configurations anyway. Now, we are going to discuss about periodicity, periodic properties and their variations in the periodic table. First, what is meant by periodicity? Anything that gets repeated at regular intervals can be called as periodicity. Say for example, in a year, the seasons are repeated at regular intervals of time. That itself can be taken as an example for periodicity. In case of periodic table, the properties of elements are repeated at regular intervals of atomic numbers. So, that phenomenon is taken as a periodicity. The intervals in which the properties are repeated are 2, 8, 8, 18, 18, 32. As the properties are repeated at these intervals of atomic numbers, these numbers are called as magic numbers. And the properties that get repeated at these intervals are called as periodic properties. A total of 9 such properties have been identified, which get repeated themselves at these regular intervals. First one is atomic radius. From atomic radius, we can calculate atomic size also, because atoms, they are supposed to be spherical in shape. So, if you know atomic radius, From that we can calculate atomic volume, which is taken as equal to atomic size. Then second periodic property is ionization potential, also called as ionization energy as well as ionization enthalpy. Next property is electronegativity. In short, it is called as EM. Then electropositivity, in short called as EP. Then metallic character and non-metallic character. Acidic nature and basic nature of oxides. Electron affinity. Electron affinity is also called as electron gain enthalpy, in short represented as EA. Next is diagonal relationship, and last one is valency. So these 9 properties get repeated themselves at regular intervals of atomic numbers. However, this property diagonal relationship is a limited property. Limited in the sense it is observed in only 2 periods of the periodic table, that is second period and third period, and the phenomenon is observed in the starting elements of only 4 groups, that is 1A, 2A, 3A and 4A. That is why diagonal relationship is sometimes not considered as a periodic property. The remaining 8 properties are applicable throughout the periodic table, and hence they can be considered as periodic properties. A detailed study of these 9 properties has to be done, and how these properties change along a period down the group, and what is the reason for that change, that is what has to be studied in detail.